Hey YouTube, DC Physics here. I was told by some students that's how I'm supposed to start these, so there we go. So what we're going to do today is a combined series and parallel circuit, and we're going to find everything out about it. I gave you the battery, it's a 12-volt battery, attached to this circuit of various resistors, and I want to figure out what's the voltage and current for each of those resistors. So how much voltage is actually dropping across this 24 ohm resistor? How much current's actually going through it? Okay, and we'll find that for all of them. So I'm going to walk you through this process. So the first thing we need to do a little review. What's a series and what's in parallel? So series means I have multiple resistors on the same path. Now when I talk about a path, I mean, say start at a battery and end at a junction. So there's only one resistor on that path. Or I start at this junction and I go to this junction. Only one resistor. Okay, start at this junction, only one resistor. So if you try all the possibilities there, you're going to find nothing is actually in series. So I don't have any two resistors that are purely in series. So what's the other option? Parallel. Parallel means there's multiple paths between points and only one resistor on each path. So if I pick, say, this junction and this junction, I could either go through R3 or I could go through R4. So that means that R3 and R4 are in parallel. But I can't go from this junction to this junction through R2 because I'll end up having to go through more than one resistor, so they wouldn't be in parallel. So what we're going to do is we're going to start simplifying the circuit down step by step and remembering what type of simplification I did. Did I do a parallel? Did I do a series? Because we're going to need to use that information to get back to find these values. So let's start. So I have R3 and R4. We just determined those were in parallel. So what I'm going to do is I'm going to focus in on that and I'm going to combine those together. All right. So I'm going to move into a new circuit and I'm going to use a parallel combination. All right. So let's draw my new circuit. So instead of drawing these two, I'm just going to draw a single resistor there. So I still have my 12-volt battery. Comes up to my R1 and hits that junction, but now I only have a single resistor there instead of the two. So I have my 12 volts, I have my R1 value, I have my R2 value, I have my R5 value, which was 4 ohms, and I have this new R value. I'm just going to call it RA. Because it's the first one we found. So I use numbers over here, so I'm going to use letters now. Because it's in parallel, I'm going to have to add these two resistors in parallel. So you'll remember that 1 over R3 plus 1 over R4 is how I add in parallel to get the new RA value. All right, so I can type this into my calculator. I find out that my new resistance RA is going to be 8 ohms. All right. Just a reminder for you, to type that in your calculator, we are going to be using that inverse key. And so you would type in 12 inverse plus 24 inverse quantity inverse to get that 8 ohms. Okay. All right. So we've simplified it down. It's not as complex as it was before. All right, now I'm going to look. Do I have any new parallels or new series that have popped up after I did this? Well, do I have any single paths that have multiple resistors? Yes, I do. RA and R5 are now multiple resistors on one path. So what I'm going to do is I'm going to combine those together. All right. So I'm going to use a series in this case, combination. All right. So I'm going to redraw that circuit. So I still have my R1 value. Still have that point, and then it goes up. R2 is up here, but now those two resistors have now melded into a single resistor, which I'm going to call RB. All right, so this was R2. Now, because this is a series combination, I'm just going to add those two resistors together. So RA plus R5 equals RB. So 8 and 4. that tells me that RB is going to be 12 ohms. R2 was our 6 ohm one. All right. And so you kind of see what we're doing here. We're starting with something complex, we're looking for series and parallel groups, and we're shrinking our circuit down. I now look and I say, okay, I have a parallel group. All right, let's combine those together. Okay. So I have a parallel group, so I'm going to redraw this. So now I have my 12-volt battery. I have my R1, which was 8 ohms. And now I have just a single resistor sitting there, RC. Now this was parallel, so RC is going to equal these two inverse added together, so 6 inverse plus 12 inverse, and inverse that. And so we end up with RC being 4 ohms. Just a good check for you as you're doing this. Whenever you have parallels, you should get a number that's less than the two numbers you started with. So like here I had 6 and 12 and I ended with 4. So I should end with a number less. Here I had 12 and 24, I ended with 8. Get a number less. Okay? When you do series, you should end up with a bigger number because you're just adding them together. All right, and then our last step here, these two values are in series. All right. And my last circuit, I have now simplified this circuit down into a single resistor of, what did this come out to be? 12 ohms on a 12-volt circuit. Okay? And so what we've done is we've simplified it down to a point where I can just use Ohm's law. And I can find everything out about the total circuit. All right. So I can use Ohm's law, so V equals IR. And so I know the voltage and the resistance, so the current comes out to be 1 amp. Okay. So this is what we call the equivalent resistance of the circuit. So if I was to look at this whole circuit as a whole, it's overall just 12 ohms. And if I look at the current's going to come out of here and it's going to be 1 amp. And it might split here, but all together it's going to be just 1 amp. So I know about the circuit as a whole. Now I want to find it out into the pieces. All right, so now I'm going to go backwards. All right, so when I go backwards, it's important that I remember these series and parallel points that I made. All right, so now when I go backwards, because it was series, that means they're going to have the same current. Okay, so I found the current to be 1 amp. So now both of these resistors have 1 amp in them. All right. So what does that mean for me? Well, that means that resistor 1 has 1 amp in it. Okay. And so does resistor C, but resistor C isn't on my list. Okay. So I can find the voltages. So they have the same current, and then you find voltage. That's if it's a series. Okay, so if it's a series, they're going to have the same currents. I use the current I just got, and I find their individual voltages. All right, so voltage 1 is going to be the current times resistance 1. So voltage 1 is going to be 1 times 8, so 8 volts. Okay. The voltage in C is going to be the current times the resistance in C. So the voltage in C is going to be 1 times 4. And so 4 volts. Now what I should see is because this is a series, the voltages should add up to the total voltage I had. So 8 and 4 add up to 12. It's a good check. All right, so I now know V1, voltage 1 is going to be 8 volts. So of the 12 volts I had available, 8 of them get used up on the first resistor. That means all of these resistors are only getting 4 volts because all of these resistors are what I called RC. All right, keep moving back. So now I had a parallel. All right, so now when I have a parallel, parallel means they have the same voltage and that means then I need to find the current. So when I go backwards, which one am I going to use? Am I going to use voltage 1 or voltage C? Well, when I go backwards, I'm looking at what group did I do the parallel to, and that was RC. So I'm going to use voltage C. So both R2 and RB have 4 volts on them. Okay? So this one has 4 volts, this one has 4 volts. Okay? And the idea, one thing you can use to check, so this had 8 volts, this had 12 volts. So no matter what path I take, start with 12, I lose 8, lose 4, I'm back to 0. Start with 12, lose 8, lose 4, back to 0. That's the loop rule. You should always get back to where you started. Okay? All right, so they have the same voltage. Now I need to find the current. So to find the current in R2, so the voltage in C is going to equal the current in 2 times R2. All right, so I have 4 divided by R2, so I have 4 divided by 6 would give me my current in 2, and so I get 2/3 of an amp. RB would be next, so then the voltage in C is going to be the same as the voltage in RB here. So then I have the current in B times RB. So the current is going to be the voltage 4 divided by the resistance 12, and so I get 1/3 of an amp. Now, just the same as I checked to make sure that my voltages added up to the previous one when I had series, I'm going to make sure my currents add up to be the previous one when I do parallel. All right. This is a pattern. Okay. So now I know my I2s and my voltage 2s. Okay. So 2 is going to be 4 volts, and the current in 2 is 2/3 of an amp. All right. Moving back. So now it was a series. Okay, so what do we do for series? Oh, series, same current, find voltage. So what did we reduce in order to find a series? Okay. We reduced these two. So these are going to have the same current as what they reduced to, RB. So both of these have 1/3 of an amp in them. Okay. So when we go backwards, we're going to look at the same current. We're then going to find our voltage. So the voltage in A is going to be my current in A times my resistance A. We're solving for voltage, so I just need to plug in my numbers. So VA is going to be 1/3 times 8. So I get 8/3 of a volt. Okay. For the other one, same kind of deal. So voltage in 5 is going to be the current in 5 times the resistance 5 of resistor 5. And so my voltage for 5 is going to be 1/3 times 4. And so I get 4/3 of a volt. And again, we can check this to make sure that we're on track. So 8/3 plus 4/3 gives you 12/3 or 4 volts. Is that what we started with before? Yes, 4 volts. Okay. All right. So we're moving on a little bit. We got our 5 values. So we had 1/3 of an amp, and we had 4/3 of a volt. All right, last step. Here we go. So last step, it was a parallel, so that means we have the same voltage. Find current. All right, with that said, they will both have the same voltage. Our voltage on the thing these two combined together to be, which was A, our voltage was 8/3. So we have V is equal to 8/3 for both of these. And so we set it up. Current is going to equal voltage divided by resistance for these two. So we're going to have 8/3 divided by 12 and 8/3 divided by 24. And so both of them have my 8/3, so I'll record that voltage. 8/3 of a volt, 8/3 of a volt. And then we do our kind of calculations. So I3 is going to be my 8/3 divided by my resistor 3, which is 12. And then my other one down here, I4, is going to be 8/3 divided by 24. These come out in the ninths, I believe. So this one comes out to 2/9. And this one comes out to 1/9. Just double check that. Yep, of an amp. 1/9 and 2/9, they go together to make 1/3. 1/3 of an amp. Yes, that's where we started. And so I end up with 2/9 of an amp and 1/9 of an amp. And if you're ever going to double check some of this stuff, you can think about, all right, I have two resistors, a 12 ohm and a 24 ohm. Which path is most of my current? Well, we can even open this up to 6 ohm, 12 ohm, 24 ohm. Which way is most of my current going to go? Which is the path of least resistance? 6 ohms. How many are going through my 6 ohms? 2/3 of an amp. Oh, that's quite a bit. How about 12, 2/9 or 1/3 of an amp? Or not even, I'm sorry, 2/9 of an amp. And then 1/9 of an amp goes through here. So we're good. So just to recap this whole process, find parts that are in parallel, find parts that are in series, combine resistors till you get down to one resistor. Okay? Find the total voltage, total resistance, total current, and then start working backwards. If it was a series reduction you did, same current, find the voltage. If it was a parallel reduction, same voltage, find the current. And you can solve for all of those parts. There you go.